Now that we understand Agentic AI at a conceptual level, the next step is to explore how these ideas translate into actual solution design. In this video, we are going to look at solution design pillars, the architectural elements that make Agentic AI applications practical, reliable, and powerful. We'll focus on three major pillars. Together, these give us a clear and repeatable way to think about designing and building intelligent systems. This video is a high-level introduction to each pillar before we go deeper into examples, design patterns, and real applications. LLMs unlock three core capabilities that Agentic AI applications can build on. First, a conversational interface. This gives us a fundamentally new way to interact with software. Instead of navigating menus or learning commands, we simply ask for what we want in natural language. For many use cases, this interface is more intuitive, more accessible, and more efficient. Second, raw intelligence for reasoning and planning. LLMs provide the intelligence needed for logical reasoning, problem solving, and multi-step planning. And this unlocks a new kind of control flow, an agentic control flow, where the system can decide what to do next, evaluate results, and adapt its actions. We'll explore how these reasoning outputs are embedded inside agentic applications and used to guide decision-making. Third, memory and context. The model itself contains learned knowledge, but it can also use external information that we provide. Techniques like retrieval augmented generation allow agentic systems to bring in documents, data, or domain-specific knowledge and apply intelligence on top of it. We'll look at how these memory techniques work and when they become available. Together, these three capabilities, the conversational interface, reasoning and planning with agentic control flow, and memory, form the foundation of practical, reliable, and powerful Agentic AI applications. On this image, from right to left, we see a progression of human-machine interface. It begins with the keyboard, where interaction is fully textual and requires knowing the right commands. The mouse introduces graphical interface, a major step forward, letting users point, click, and navigate visually instead of typing everything. Multi-touch takes this further, allowing direct manipulation with fingers and gestures like swipe, pinch, and drag. For many years, this was the most intuitive and natural interface we had. Now we have the conversational interface. Instead of selecting from menus or learning commands, we simply express what we want in natural language, the same way humans communicate with each other. This removes many limitations of traditional interfaces and make interaction far more flexible and expressive. There are even closer interfaces such as brain-computer interface, but these are not natural for everyday use and remain suited mostly for special circumstances. So for most real-world applications, a conversational interface is as natural and human-friendly as an interface can get. And it can still be combined with touch or visual interfaces when needed to maximize possibilities. A conversational interface that is actually robust enough for real use is something we now have access to. This interface is very natural for humans. We simply describe what we want in language and refine it through conversation. In many cases, this works better than forms, menus, or command-based interfaces. There is also an important additional insight. Just as LLMs enable a conversational interface between humans and machines, an emerging capability is that LLMs can also mediate communication between machines. You can think of this as a fuzzy machine interface. Instead of relying only on rigid APIs and strict schemas, LLMs can interpret API documentation, generate requests dynamically, handle incomplete or unstructured responses, and adapt their communication strategy on the fly. This means machines can interact more flexibly, discovering how to call a service, translate between formats, or coordinating with other systems even when the interfaces aren't perfectly aligned. It is still an emerging field, but early systems already demonstrate this behavior in practice. The conversational adaptive LLM mediated communication represents a new way software systems can interact. To understand another pillar that makes agentic AI different, it helps to look at how control flow in software has evolved. We begin with imperative model. In imperative systems, the computer is told exactly what to do, step by step. Traditional programming works this way. Next is the declarative model. Instead of spelling out every step, we define the goal and the system figures out the path. Examples include SQL or logic programming. We describe what we want, not how to do it. Now we can introduce what we can call an agentic control flow. Here we still provide a goal, but also context, and the system uses reasoning and planning to decide what comes next. It can break a problem into steps, evaluate results, switch strategies, and adapt. Behavior traditional systems cannot perform on their own. So in summary, in an imperative control flow, you tell the system every step. In a declarative control flow, you tell the system the goal. And in an agentic control flow, you provide the goal plus the context, and the system reasons, plans, and adapts. This shift from executing instructions or accomplishing known goals to autonomous decision-making is a fundamental capability enabled by large language models. The third pillar that enables agentic AI systems is memory and context. LLMs come with a large amount of learned knowledge. But in real applications, we often need information that goes beyond what the model was trained on. We might need internal documents, user-specific details, product data, regulations, or live information that changes over time. To make this possible, we can provide additional context to the model. The most common approach is retrieval augmented generation, where the agent retrieves relevant documents or facts and combines them with its reasoning. This means the agent is no longer answering purely from its training data. It can reason on top of precise external information. There are also more lightweight techniques. Keeping short-term memory inside the conversation, maintaining long-term vectors in a memory store, or storing structured knowledge it can query when needed. All of these allow the agent to stay context-aware, accurate, and domain-specific, instead of being generic. So together with the conversational interface and the agentic control flow, memory and context give us a system that can understand, reason, and act using the information that actually matters for the problem. To make this more concrete, here are a few examples of how memory shows up in real agentic systems. A customer support agent can retrieve relevant documents from a knowledge base and answer questions based on accurate internal information, not just what the model learned during training. A research assistant can search through private PDFs, reports, or uploaded files and reason over them to produce summaries, insights, or answers. An agent performing tasks can store short-term memory, for example, remembering what it has already tried, so it doesn't repeat steps or make the same mistakes. And a personalized assistant can build long-term memory of user preferences, history, and context, making its responses more personalized and useful over time. So memory isn't abstract. It's what allows agents to be accurate, context-aware, personalized, and useful in real-world environments. Memory comes in several forms. Short-term memory lives inside the conversation. Long-term memory can be stored in a vector database, and drag brings external documents into the model. And structured data access lets the agent query systems like SQL or APIs. Together, these give the agent the ability to work with information the model never trained on but can use intelligently. In summary, we introduced 3 architectural pillars that make Agentic AI practical, useful, and powerful. First, the conversational interface. It's a natural way of interacting with software, not by clicking menus or learning commands, but simply by expressing what we want. Second, agentic control flow. Instead of executing predefined steps or static goals, the system can reason, plan, and adapt based on the situation. And third, memory and context. By bringing in documents, data, or previous interactions, the model can operate with accurate, task-specific knowledge rather than relying on what it was trained on. Together, these 3 pillars form the foundation for designing agentic AI systems that are intuitive to use, intelligent in their behavior, and grounded in real-world information.